Welcome, cosmic explorers, to a mind-blowing journey into one of the universe's deepest mysteries. Today, we're diving headfirst into the enigma of dark energy, the mysterious force driving the cosmic expansion of our universe. Imagine a power so vast, so elusive, that it's pushing galaxies apart, stretching the fabric of space itself, and shaping the fate of everything we know. What is dark energy? How did we discover it? And why does it hold the key to the future of the cosmos? Buckle up, because we're about to embark on an epic adventure that will stretch your imagination and leave you burning with curiosity. Let's unravel the mystery of dark energy together. Picture the universe, a vast, ever-changing tapestry of stars, galaxies, and cosmic clouds, all born from the Big Bang 13.8 billion years ago. For a long time, scientists thought they had a decent grip on its story. The universe began with a bang, expanded, and gravity, tugging on matter, would either slow that expansion to a crawl, or maybe even reverse it, collapsing everything back in a big crunch. But in the late 1990s, a shocking discovery turned that picture upside down. The universe isn't just expanding, it's speeding up, accelerating like a car flooring the gas pedal. The culprit? A mysterious force we call dark energy, an invisible driver pushing the cosmos apart. This revelation rocked science, and it's one of the most thrilling puzzles we've ever faced. Doesn't that make you wonder what's out there, secretly steering the universe? Let's rewind to the beginning of this cosmic detective story. The idea of an expanding universe isn't new. In the 1920s, Edwin Hubble, an American astronomer, observed that light from distant galaxies was redshifted, stretched toward the red end of the spectrum. This meant galaxies were moving away from us, and the farther they were, the faster they fled. This discovery proved the universe was expanding, a key piece of the Big Bang theory. For decades, scientists debated what would happen next. Gravity, pulling on stars, gas, and everything else, should slow the expansion over time. Some thought it might stop and reverse, crunching the universe back. Others pictured a steady coasting, slowing gradually. But no one expected what came next. What could possibly overpower gravity on a cosmic scale? The bombshell dropped in 1998, thanks to two teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team. They were studying type Ia supernovae, exploding stars that shine with a consistent brightness, making them perfect, standard candles, to measure cosmic distances. By tracking how their light dimmed and redshifted, the teams could map the universe's expansion history. What they found was jaw-dropping. Galaxies weren't just drifting apart, their separation was speeding up. Distant supernovae appeared fainter than expected, meaning they were farther away than a slowing or steady expansion could explain. Something was accelerating the universe, pushing galaxies apart faster and faster. The teams dubbed this mystery force dark energy, and it changed cosmology forever. Isn't it wild to think a hidden force was hiding in plain sight? So, what is dark energy? Here's the honest truth, we don't fully know. It's a placeholder term for whatever's driving this cosmic acceleration. Scientists estimate dark energy makes up about 68% of the universe's total energy content, dwarfing the 5% from ordinary matter, stars, planets, us, and the 27% from dark matter, the invisible stuff shaping galaxies. Unlike matter, which pulls things together via gravity, dark energy acts like a repulsive force, stretching space itself. It's invisible, doesn't emit or absorb light, and seems to be everywhere, woven into the fabric of the cosmos. But its nature? That's the million-dollar question, and it's what keeps cosmologists up at night. How can something so powerful be so elusive? Let's explore the roots of this idea. Dark energy has a surprising ancestor in Einstein's theory of general relativity, published in 1915. Einstein described gravity as the warping of spacetime by mass and energy. When he applied his equations to the universe, he found a problem. They suggested the cosmos should expand or collapse, but at the time, everyone assumed the universe was static, eternal, and unchanging. To fix this, Einstein added a term called the cosmological constant, a kind of fudge factor to balance gravity and keep the universe steady. Later, when Hubble showed the universe was expanding, Einstein called this his greatest blunder. But here's the twist, that cosmological constant might be dark energy in disguise, a repulsive force counteracting gravity. Did Einstein stumble onto a cosmic truth by accident? Now, let's dive into the leading theories about dark energy. The simplest idea is that it's the cosmological constant, a uniform energy baked into the fabric of spacetime. This energy has a negative pressure, pushing space apart. Its value, though tiny, is constant everywhere, driving the acceleration we see. Observations of supernovae, galaxy clusters, and other data fit this model well, and it's part of the standard picture of cosmology, called the lambda cold dark matter model, or LCDM. Lambda stands for the cosmological constant, and cold dark matter shape structure. But there's a catch. Quantum physics predicts a value for this energy, called vacuum energy, from particles popping in and out of existence, that's astronomically larger than what we measure. This mismatch, dubbed the cosmological constant problem, is a huge puzzle. Why is dark energy so weak when theory says it should be enormous? Another theory is that dark energy isn't constant, it's dynamic, changing over time. This idea, called quintessence, imagines dark energy as a field, a kind of cosmic fluid that varies across space and time. Unlike the cosmological constant, quintessence could evolve, perhaps growing stronger or weaker as the universe ages. Some models suggest it interacted with matter or dark matter in the early universe, shaping its history. Observations haven't ruled this out, but it's harder to test. Other wild ideas exist too. Maybe dark energy is an illusion, a flaw in gravity's laws on cosmic scales, or a sign of extra dimensions from string theory. Each possibility tantalizes us, begging the question, what's really driving the cosmos apart? Let's look at the evidence, because science demands proof. The 1998 supernova discovery was the spark, but more clues piled up. The cosmic microwave background, or CMB, the afterglow of the Big Bang, offers a snapshot of the universe at 380,000 years old. Satellites like WMAP and the Planck spacecraft map tiny temperature variations in this light, revealing the universe's composition: 5% ordinary matter, 27% dark matter, and 68% dark energy. These ratios, combined with the expansion rate, fit the accelerating model perfectly. Another clue comes from galaxy clusters. The number and growth of these massive structures depend on gravity and expansion. Surveys show fewer clusters than expected in a slowing universe, pointing to dark energy's push. Isn't it amazing how many threads tie back to this mystery? One of the coolest pieces of evidence is baryon acoustic oscillations, or BAO. In the early universe, sound waves rippled through the hot plasma, driven by gravity and radiation. As the cosmos cooled, these waves froze, leaving a pattern in how galaxies are spaced today. Surveys like the Sloan Digital Sky Survey map this pattern, a cosmic ruler measuring expansion. The data shows acceleration, consistent with dark energy. Gravitational lensing, where massive objects bend light, also helps. The warping of light by galaxy clusters reveals the universe's geometry, and it's flat, fitting a model where dark energy dominates. Each clue builds the case, making you wonder, what other signs are out there? Let's explore dark energy's role in the universe's story. After the Big Bang, the universe expanded rapidly, driven by inflation, a brief, explosive stretch. For billions of years, gravity from matter and dark matter slowed this expansion, pulling things together to form stars and galaxies. But around 5 or 6 billion years ago, something shifted. Dark energy's repulsive force overtook gravity, and expansion began to speed up. Today, galaxies race away from each other, and the farther they are, the faster they go. This acceleration reshapes the cosmic web, filaments, walls, and voids of galaxies, stretching it apart. Dark energy is the universe's new driver, and its influence is growing. How did this cosmic handover happen? To understand this, let's dive into the universe's composition. Ordinary matter, protons, neutrons, you and me, makes up just 5%. Dark matter, the invisible stuff holding galaxies together, is 27%. Dark energy, at 68%, rules the roost. Early on, matter dominated, slowing expansion as gravity pulled. But as the universe grew, its volume increased, and dark energy, tied to space itself, grew in strength. If it's the cosmological constant, its density stays fixed, so as space expands, its total push gets bigger. By billions of years ago, it flipped the script, accelerating the cosmos. This balance fascinates scientists, because a slightly different amount of dark energy could have made the universe collapse or fly apart too fast for galaxies to form. Are we here by cosmic luck? Let's talk about how we measure dark energy. The 1998 supernova studies used Type Ia supernovae, reliable distance markers, to track expansion. Today, projects like the Dark Energy Survey use telescopes to map millions of galaxies, measuring their positions and speeds. The Vera C. Rubin Observatory, coming online soon, will scan billions more, tracing dark energy's effects through lensing and galaxy distribution. The Euclid satellite, launched by the European Space Agency, probes the cosmic web, using BAO and lensing to pin down dark energy's behavior. Each tool refines our picture, testing if it's constant or changing. The precision is stunning, yet the mystery lingers. What new clues will we uncover? Now, let's ponder the universe's fate, because dark energy holds the reins. If it's the cosmological constant, expansion will keep accelerating. Galaxies will drift farther apart, stars will burn out, and trillions of years from now, the universe could face a big freeze, a cold, dark, dilute end where everything's too far to interact. But if dark energy is quintessence and grows stronger, we might face a big rip, where galaxies, stars, even atoms get torn apart by runaway expansion. Or, if it weakens, gravity could win, collapsing the cosmos in a big crunch. Observations lean toward the big freeze, but the future's uncertain. Doesn't that make you wonder where we're headed? Let's explore the challenges. The cosmological constant problem haunts us. Quantum theory predicts vacuum energy 10 to the 120th power times larger than what we see. Why this tiny value? Some invoke the anthropic principle, suggesting our universe is one of many in a multiverse, with dark energy tuned just right for life. Others seek new physics, like string theory or modified gravity, to explain it. Another puzzle. Does dark energy interact with dark matter or matter? Some models of quintessence suggest ties, shaping cosmic history. These questions push the edge of science, blending cosmology, particle physics, and quantum mechanics. The unknown is thrilling, isn't it? Let's bust some myths. Dark energy isn't a force like gravity, it's a property of space, driving expansion through negative pressure. It's not dark matter, which clumps and pulls via gravity. Dark energy pushes, uniformly spread. And no, it's not science fiction. Supernovae, the CMB, lensing, and BAO give solid evidence. Some wonder if it's aliens or cosmic magic, but science sticks to testable clues. The real story is wilder than fiction, a mysterious force, ruling 68% of the cosmos, steering its destiny. Doesn't that fire up your curiosity? How does dark energy tie to us? It's shaped the universe we live in. Without its delicate balance, galaxies might not have formed, stars might not have ignited, and life might not exist. The atoms in your body, forged in stars, owe their home to a cosmos where dark energy didn't overwhelm early growth. Today, it pulls galaxies apart, but we're safe in the Milky Way, bound by gravity. Still, dark energy connects us to the universe's grand saga, from the Big Bang to an unknown future. We're part of this cosmic dance, driven by a mystery we're racing to solve. Let's look at the human side. Dark energy's story is our story, a testament to curiosity. From Hubble's redshift to the 1998 supernova breakthrough, scientists like Saul Perlmutter, Brian Schmidt, and Adam Rees, Nobel winners in 2011, pushed the boundaries. Thousands now work on surveys, telescopes, and theories, chasing this enigma. It challenges our tools, our math, even our imagination. Yet, it unites us with the cosmos, urging us to ask, why this universe? What drives it? Our quest for answers is a journey of wonder, and you're part of it. As we near the end, let's gaze forward. Dark energy remains mysterious, but each observation, supernovae, the CMB, galaxy maps, brings clarity. Future missions like Euclid, the Rubin Observatory, and the Nancy Grace Roman Space Telescope will probe deeper, testing if dark energy's constant or evolving. Could it reveal new physics? Might it tie to quantum gravity or a multiverse? The possibilities dazzle, and the chase is on. What questions does dark energy spark in your mind? How will we crack this cosmic code? Thank you for joining me on this epic dive into dark energy, the mysterious force driving cosmic expansion. I hope your curiosity is blazing. If you love this cosmic adventure, hit that like button, subscribe, and ring the bell for more journeys into the unknown. Drop your thoughts in the comments, What blows your mind about dark energy? What mysteries should we explore next? Until then, keep looking up, keep wondering, and let's unravel the universe together. See you in the next video, Cosmic Explorers.